Welcome to this week's reset. We are very happy to have Andreas Kleiner, who is going to present optimal delegation in the multidimensional world. And we are also very grateful to our panelists, Alexander Frankel and Ricardo Alonso, who are going to ask some questions. We don't have co-authors today, so I guess there's not too much point of leaving comments in the chat. So if you have a pressing comment, you can, or a question, you can unmute yourselves or wait until after the talk to ask. Yeah, so let's get going.
Okay, thank you everyone for being here, and thank you Alex and Ricardo. So I look forward to getting any comments here, so please just ask questions even so I cannot monitor the chat. So this project is about the optimal delegation model by Holmström. For those of you who haven't seen it in a while, let me give you a brief reminder. So there's going to be a principal who's going to take an action, but what's the right action depends on some unknown state of the world. The principal doesn't know this state of the world, but there's an agent who has this as his private information. The problem is how can the principal elicit this information in a world where there are no transfers? And since preferences are misaligned, the agent might be strategic in revealing the information. And then the question is how to optimally design a mechanism to make use of this information to make good decisions. So following this work by Holmström, there has been a fairly large literature analyzing this question both theoretically, but also applying to all kinds of settings in economics and also in political science. For example, the problem has been used to study organizations, to study how we should regulate monopolists, has been used to study trade agreements, and more in the political science area has been used to study bureaucracies, for example, when Congress delegates decisions to some agencies, or has been used to study bargaining. So the theoretical analysis has mainly been focusing on a one-dimensional model where the state of the world is one-dimensional, just some number, and also the action that the principal takes is just some number. But for some of the applications, it seems very natural that actually the decisions that we delegate are fairly complicated. For example, when we decide on a trade agreement, this is typically a fairly complex object where we have to make all kinds of decisions. Or when we delegate decisions to the EPA, also these are typically complex decisions that are hard to capture with just a single dimensional state. So for these reasons, I'm interested in analyzing a multidimensional version of the delegation problem where both the action and the state of the world are multidimensional. And I think this could be interesting for various reasons. So one would be that hopefully we can develop some tools that can then be used to study specific applications and see what's optimal if we model such applications in a multidimensional framework. I think it could also be interesting trying to understand better how robust or fragile the results are that we find in one-dimensional models. So if we make the analogy to a multi-product monopolist, for example, there we see that the results that we get in a multi-product setting are quite different compared to a single product monopolist. I find it interesting to get a sense of how fragile the results are that we get in the one-dimensional delegation problem. And I'm trying to argue that the tools that are very natural in the multidimensional setting are actually already useful in the one-dimensional setting and give us some new insights and maybe simplify our life a little bit. And maybe finally, from a slightly more theoretical perspective, this problem that we're going to see is a fairly standard multidimensional mechanism design problem. And in general, we don't know too much about what are optimal mechanisms in multidimensional mechanism design settings. And what we do know is almost everything is essential for the multi-product monopoly setting. So one hope could be that one can also make progress by analyzing the different kinds of settings to get a bit of sense what's specific to a multi-product monopoly setting and what holds more generally in multidimensional mechanism design. So this is kind of what was my motivation to start on this project. And to make things a little bit more concrete, let me start with a simple example. And the example will first be a one-dimensional one. So there will be a one-dimensional state of the world. This will be just, let's say, the unit interval. And we're going to assume that the state here is uniformly distributed between 0 and 1.
So, sorry, are you sharing your screen? Because I'm not seeing the slides.
I think I am.
I'm seeing it, no problem.
Yeah.
I mean, it's okay with me if you go without slides. I mean, it's very entertaining, but
Ricardo, I
Ricardo,
don't know how I can.
We
I
are
think there are
broadcasting
slides.
to YouTube. I can send. I will put the link in the chat.
Very good. So in this example, let's start with a one-dimensional state of the world that's uniformly distributed between 0 and 1. And I'm going to assume that the principal and the agent both have quadratic payoffs. So this means I'm going to normalize that the agent's ideal point is just the state of the world. So the agent would always like to take an action that's equal to the state of the world and has quadratic loss function. But the principal's ideal point is different. So these are the misaligned preferences. And in particular, the principal's ideal point will be the state minus some positive number beta. And so the literature on this question gives us precise sense of what will be an optimal mechanism in this setting. And the optimal mechanism can here be implemented in an indirect way as interval delegation. So the optimal mechanism you can implement here by the principal telling the agent, I'm going to delegate the decision to you, and you can take any action that you want out of a menu of actions that I suggest to you. And in this particular example, the optimal menu will be just an interval. It starts at 0 and goes up to some number. So the agent is going to be allowed to take any action out of this red line segment. So this means, for example, if the realized state of the world is fairly low, the agent can pick her first best action. And for high states of the world, the agent will be constrained and is going to pick the highest action that's still in the red set. And so this severely, in some sense, it severely restricts the agent, because in a high state of the world, actually both the principal and the agent would like to take higher actions. The problem is if the principal would allow the agent to take these higher actions, then the agent would take them too often. This kind of sense why that we want to restrict the agent quite a bit. And so this is what's optimal in a one-dimensional world. And now the simplest setting in a multidimensional setting could be the following, where now let's see what happens if the state of the world is two-dimensional and let's say it's uniformly distributed on this unit square. And again, the agent would like to take an action that's equal to the state of the world, and the principal has some bias beta, let's say could be strictly positive in both directions, so strictly negative. So the principal always wants to have lower actions in both dimensions. So then the question would be, what could be optimal mechanisms in this setting? Kind of a first guess might be that, okay, one thing that I for sure could do is I take the idea of interval delegation and do it in both dimensions. So that would give me this red square. And so one idea would be I could allow the agent to take any action that's in this red set, but nothing outside of it. So again, for low states of the world, the agent would get her first best outcome, but for high states, the agent would be restricted quite a bit. And then a key idea that arose at various points, I think, in mechanism design is that once you have these multidimensional settings, often you can do better by linking these two problems, the two dimensions, even so they might otherwise be independent. So here the optimal action in dimension 1 doesn't depend on what's the state in dimension 2 or what's the action we state in dimension 2. This is due to the quadratic payouts. Still, the principal can do better here by offering something of the similar form. So we argued that in a very high state of the world, let's say in dimension 1, actually it would be better for both the agent and the principal to take a high action. Still, in one dimension, you wouldn't want to give this option to take high actions to the agent. But now with 2 dimensions, the principal could say, okay, if you really want to take a high action in dimension 1, you can do so, but only if you take a very low action in dimension 2. And maybe this gives a rise to this kind of budget mechanisms that, for example, Andreas has looked at. And more generally, this idea has been explored, for example, by Jackson and Sonnenschein, how you can link independent decision problems to make better decisions. And the question will then in this setting, okay, this seems a clear way to improve upon just delegating the square, but what's the optimal way? And in principle, now there are many more and more complicated mechanisms that you could think of that take all kinds of complicated stochastic decisions and so on. So I will be interested in what's optimal in this setting and what will turn out, and hopefully I can give you the main idea towards the end of the talk. In this setting, the optimal mechanism will look fairly similar to this budget mechanism, just this boundary, exactly what decisions the agent can take will look slightly different. So the optimal mechanism, again, can be implemented in this delegation that the principal tells the agent, you can take any decision that lies below this solid blue curve, but nothing above it. And then this is the optimal way kind of to bundle these two independent decision problems from the principal's perspective. So the outline of the talk will be, I'll introduce the basic model that's fairly standard, and then I'll spend quite a bit of time to discuss about what are the feasible mechanisms here to find a good characterization of all incentive compatible mechanisms. The main result will be a characterization of when a given mechanism is optimal, and I'll try to give you some ideas what one could hope to find that conditions under which some simple mechanisms are optimal in this framework. I'll be very brief on the literature. So following Holmstrom's work, there has been a significant literature analyzing these questions in a one-dimensional framework with some beautiful contributions, for example, Ricardo's work or Amador and Beckwell. But we know relatively little about the multidimensional delegation framework. So there's some paper where only the state or only the actions are multidimensional. I think Alex's paper, as far as I know, is the only paper where there's truly a multidimensional action and a multidimensional state of the world. So Alex has a very elegant paper where he looks at the specific setting, where he finds an elegant trick to see that in his case, half space delegation will be optimal. The tools that I'm going to use are relatively standard. Some are fairly old from the multidimensional mechanism design literature, especially Rocher's characterization of incentive compatibility. So if there are no questions, then I'll dive into the model. Very good. So there's going to be the principal who takes an action A, and the action can be any element of Rn. So this is an n-dimensional action vector. There's going to be a state of the world, which I denote by S. It lies in some set capital S, and again, this is in a subset of Rn. And the state of the world is the agent's private information. Sometimes I call it the agent's type. Now, the payoffs of both the agent and the principal are going to depend on the state of the world and the action. And I'm going to assume a very particular functional form, and then I'll explain why I do that and where this is useful. So the utility of the agent, if we take action A in state of the world S, is the inner product of A and S plus B of A, where B is a function which I assume that's strongly concave and differentiable. And for the principal's payoff, the utility will be the inner product of A times G of S plus B of A, where G is assumed to be continuously differentiable. So what should we make of these assumptions? So first of all, I want to emphasize that one particular functional form that's included here would be quadratic payoffs, where the agent's bliss point is just the state of the world S, and the principal's bliss point would be G of S. So you can see this by, this would be the quadratic payoff. And then if you multiply things out, you get this A inner product S minus 1/2 the squared norm of A, and then minus a term that only depends on the actual state of the world. And of course, if you add this back or delete this term, this won't change preferences over the actions. So it covers the quadratic payoffs. It's more general because this B function you can use to have it some form of asymmetry, both within one dimension, but then also have to treat different dimensions differently.
Can I ask a question?
Yes.
How important is it that the state space and the action space have the same dimension here? Maybe it's trivial if not, but could you just elaborate a second?
Yes. So what's important in the functional form that I'm going to assume is one factor I'm going to use is that the agent's payoff will be an affine function in the state of the world. And that will give me a relatively simple characterization of incentive compatibility. So this is the first important thing that I hear. It's an affine function of the state of the world. And the second property that I'm going to use and that I can relax, but I think it makes the the treatment more elegant is that both the curvature in the action is the same for the agent and the principal. So this B function shows up for both terms. In the end, I can talk briefly what happens if you change this, but I think this formulation is the cleanest and the most elegant one. And now coming to your question, so it's really important that you have this linearity in the state of the world. And now if you have that the action space and the state space have different dimensions, I think there are some formulations that you can use, but it typically gets very restricted if you want to keep this linearity in the state of the world.
So it's because it doesn't allow you to use these techniques that you really needed multidimensionality, or in a sense, there's an indirect reason not to have it, the different dimensionality across the two spaces. I don't know. Okay. Anyway.
Yeah, but at this level of generality, S could have a dimension strictly lower than N, right? And that I don't see the problem that you were mentioning.
Very good. So I'm going to make assumptions on S. So you're right. So you could the dimensionality, but it would like the dimensionality of S could be smaller, but it would still be vectors in Rn. So I would still have this dot product formulation. And I don't see a way to get much more general by allowing different dimensionalities. But I think it's a very good question. Okay, so yeah, for the state, I'm going to assume that it's distributed according to some CDF capital F, which has a differentiable density small f. And I'm going to assume that the support S is compact and convex. And then in the setting following Holmstrom, so there will be no transfers. And I will be interested in what's the optimal mechanism for the principal. So if the principal can commit in this model to a mechanism and aims to maximize her expected payoff. Okay, so this is the model. It's relatively standard, so the revelation principle applies. So this allows me then to only work with direct mechanisms. So a mechanism in the setting is going to be a function that maps the reported states in S into lotteries over Rn. So I'm going to allow here for lotteries. And so the motivation for that is both theoretically, it seems interesting to do this. I think there are also a couple of applications where it's actually, even if you only care about deterministic mechanisms, it's actually very useful to know that the given mechanism is optimal in the full class of stochastic mechanisms. For example, I have a paper on bargaining where it's actually useful to have this information. I think Alex in his paper also used this, that knowing that a deterministic mechanism is optimal in the larger class of stochastic mechanisms. And I am also think that it's actually in some sense a good formulation of this problem, because what this gives me is that the space of mechanisms is actually a convex set, and somehow it's easier to optimize over a convex set instead of, if you only have deterministic mechanisms, you can have that the convex combination of two incentive compatible mechanism is not an incentive compatible mechanism. So I think this is probably the right way to go in this framework. So a mechanism M is incentive compatible if, while reporting the true state of the world, maximizes the agent's payoff. So in terms of notation, previously I defined this function B in terms of the action. Now I'm going to extend this linearly over lotteries of actions. So M of S prime will be the lottery that the agent gets if he reports that the state of the world is S prime. And if this true state of the world is S, this will be the expected payoff of the agent. So this is standard incentive compatibility. And then the first question will be how to characterize the set of incentive compatible mechanisms. So in the one-dimensional world, I think a nice approach that has been used in this literature is trying to use Meyerson's technique. The idea would be, say, I assume for now that there are transfers in this model, then essentially I can use the Meyerson characterization and the mechanism will be incentive compatible if kind of the allocation rule will be increasing and the transfers are pinned down by the envelope theorem. And then in a second step, we can put in the extra constraints that the transfers are actually equal to 0 everywhere, simply because we don't have transfers here. So this approach, for example, has been used by Amador and Beckwell. I think it's a nice approach, but sometimes it makes it harder to guess kind of the Lagrange multipliers in their framework because you have many binding constraints. So you have to guess many Lagrange multipliers. And now, moreover, in this multidimensional settings, I mean, it's well known that characterizing incentive compatibility in this way is a little bit awkward because then you have to replace this monotonicity constraint on the allocation rule by a cyclical monotonicity constraint, which is typically hard to optimize over. So instead, what Rocher proposed, I think already in the 80s, was to work with the indirect utilities of a mechanism. So this is what I'm going to do here. So given some mechanism M, I'm going to define the indirect utility U, and this will be a function that's defined on all of Rn, and this is somewhat important. So this is slightly different than in Rocher's world. So here I define U for every vector in Rn, and it's defined by this equation. It's simply the utility that an agent of type S could maximally get in this mechanism M. So here the agent optimizes by then choosing the report S prime optimally and then gets the corresponding utility from the mechanism. Yeah, now the question will be, I'm trying to characterize all incentive compatible mechanisms via these indirect utilities. So the first question will be, which indirect utilities are actually going to correspond to incentive compatible mechanisms? So what is this set of indirect utilities that I have to optimize over? And so the first observation, I think this is relatively standard in mechanism design, is because I assume that the agent's payoff function is an affine function of the true state of the world S. Now here I take the maximum over such a family of linear functions. Therefore, I get that the indirect utility U will be a convex function of the state of the world. And here, this is where it's really crucial that I have this linearity in S that I was assuming in the model. And in many mechanism design problems with transfers, this is actually the only thing that you get. For example, in Rocher and Chonet, the only condition is that the indirect utility must be convex. But here now
So very quickly, do you think that you could accommodate an interim participation constraint in this setup? So meaning that at each type is guaranteed the minimum utility just because they can walk out once they learn the information.
Yeah, very, very good question. Yes. So I mentioned it towards the end, and I think this indirect utility approach, maybe this is your dice, seems very well suited for that because these outside options we often model by giving the agents type some specific utility, right? And so this becomes now very easy. Just the utility has to be larger than some value. Yes.
Okay, thank you.
So we know that the indirect utility of any mechanism must be a convex function. But now in this world where there are no transfers, I cannot promise any convex function, right? And this is different to a setting with transfers. With transfers, I can promise you a high utility, then I simply have to pay you as the agent. But now here there's no transfers, and therefore there's somehow an upper bound on how much utility the principal can promise the agent. And in particular, what's the best possible that the agent could hope for would be that the agent simply can choose any action, the action that he actually likes, what's the best action to the agent. So this seems to put an upper bound on the indirect utility. The utility of any agent type S must be weakly less than the best that the agent could get. I define this to be this function HS, the first best payoff. And this is defined as simply the supremum over the utilities that the agent could get in this framework if he were completely unconstrained in choosing his action. Okay. And you can see just from the formulas also, here we're taking the supremum over a smaller set of lotteries, namely only those that the mechanism offers. So U of S will always be less than H of S. So clearly for any indirect utility, those two conditions must be satisfied, that U is a convex function that lies below this first best payoff. And the first result is that those are actually the only constraints that we have. In particular, U corresponds to an incentive compatible mechanism if and only if U is a convex function that lies below this first best payoff. So I think this is a relatively nice and geometric characterization, which gives you, at least for me, it helps to get a good sense of how you want to optimize. You choose these convex functions, and then you just have an upper bound on how high you can get. So this gives us some hope that you can actually work in this model with such a simple characterization of incentive compatibility. So one direction we've already seen. We've seen that if U is the indirect utility of some. Yes.
So just a very minor observation, which is I understand that the upper bound H is the one you're interested when looking at the optimal for the principal, but there's also a minimum that the agent can guarantee himself. I mean, there's a minimum utility that I can, even if the principal imposes the worst possible action on me, or is it unlimited?
Okay, very good. That's a good point. So I chose the model formulation such that the action space is unbounded. And okay. So I can give you arbitrary low utilities just because you're risk averse. And yeah, but I agree, if you think that there are exogenous constraints on what actions are feasible, then one has to adapt this a little bit and you will get a lower bound constraint. In addition,
or also the what I mentioned before, the interim participation constraint.
Perfect. Yes, exactly. That will also give you a lower bound. I view this just as a kind of I was trying to find the simplest setting, and this is then the cleanest characterization here. But yeah.
Thank you.
So we've seen that the indirect utility of any mechanism must be convex and lie below this first best payoff. So now I'm going to give you the idea why any convex function below the first best payoff will be the indirect utility of some mechanism. So here we're given the graphs that I'm going to show you. They're all going to be, or most of them will be one-dimensional graphs, but the argument also holds in a multi-dimensional setting. And on the horizontal axis, this will be the state of the world. And on the vertical axis, I'm going to measure utilities. And now the graphs will always be shown for quadratic utilities. So in that case, this first best payoff H will be just a quadratic function. This will be blue. And now green is here some other convex function that lies below this first best payoff. And to argue that the lemma holds, essentially we now have to show that there exists some incentive compatible mechanism that induces exactly these indirect utilities, so that the utility of every agent type in this mechanism will be exactly given by this green function. So let's try to construct this mechanism M. We're going to fix some particular type S. And now I have to see which lottery should this mechanism give the agent of type S to induce this green utility. So first of all, the envelope theorem applied to this green function tells us that the expected value of the lottery that this agent type S gets must be equal essentially to the slope of the green curve. Okay. So this is like a standard mechanism design. Now the question is, can we give this agent type always just deterministically this action which equals the slope of U? Well, let's see which utility this would induce. So because this is now for quadratic preferences, this slope of U, this will be exactly, this action will be the first best outcome for an agent whose type is exactly the slope of U. This is because it's quadratic utilities. So for the agent type gradient U of S, this action, getting deterministically this action gradient U of S would be the first best outcome and therefore would give you the blue utility, the first best payoff. And now we can see that therefore the agent type S, if he would deterministically get this action gradient U of S, he would get this utility up here, which lies strictly above the green curve. So here the utility would be too high. But now I can use that I have this freedom, that I have this rich action space, and that the agent is assumed to be strictly risk averse in the action. And now I can construct a lottery that has the same expected value, but gives lower utility to the agent simply by adding noise. So this is the argument that I can construct a lottery that has an expected value gradient U of S, but gives exactly this green utility to the agent. And here I'm using that the green curve lies below the blue curve really everywhere. So this is the argument I can construct now these lotteries, and this mechanism will be incentive compatible, because what happens if type S were to misreport and claim that he's type S prime, well, then he would get the lottery that type S prime gets, which has an expected utility, again, which is equal to the slope of the green curve at S prime. And because U is a convex curve, the corresponding utility for type S will be actually lower, will be the end of this dashed line, which is lower than the utility that the agent gets by being truthful in the mechanism, which will be the green curve. And therefore, this mechanism will be incentive compatible. So this is roughly the argument why for any convex curve that lies below the first best payoff, I can construct a corresponding mechanism.
And what was the assumption that got H to be convex?
Very good. So yeah, it's also driven by this assumption that the payoff of the agent is linear in the state of the world. So by the same argument as for U, we take a maximum of a family of affine functions in the state. Okay, and then so convexity of U gives us the incentive compatibility, and the fact that U lies below H ensures that we can construct these lotteries. And you can see now if U were somewhere above H, we couldn't implement the same outcome without transfers. So let's get some idea of, so from now on, I'm going to talk about these indirect utilities all the time. So let's try to get some intuitive sense of what they're showing. So this would be, what I'm showing here would be a mechanism that I've mentioned before that's called interval delegation. So here the green curve again would be this indirect utility of the agent. I'm claiming this is the indirect utility if the agent is allowed to choose any action that lies in the red set. So if the true state of the world actually lies in the red set, that's good for the agent, because then the agent can choose her first best action. So she will get a utility that's equal to the first best payoff, which is the blue curve. Now, if the state realizes very low, then the agent in this interval delegation will be constrained. He cannot choose her favorite action, so he's going to choose the lowest action that's available. So this is lowest point here, and this gives us that the indirect utility here will be an affine function, because all those types are going to choose the same action, and therefore the slope of U will be constant here, and the same on the right side of the interval. But now you can think of all kinds of other mechanisms. Here, this would be similar to interval delegation around here, but now here in this in the green mechanism, we offer some other action to the agent, and that's optimal, or that's the first best action of an agent's type around here. So this means if the realized state is not too high, those types choose the highest action in the interval, but once the state is too high, then all those types above and above will choose this newly added action. And finally, just to give you one more example, this would be another mechanism. And now what's here special is here we have several of these linear pieces in the indirect utility. And what does this piece here mean? So this piece here corresponds to some action, because here we have a constant slope. And this action is for no agent type the ideal action. Because even kind of for the agent where we get closest to the first best payoff, even this agent type would strictly prefer to get her ideal action instead of the thing that the mechanism gives me. And the reason then is that this must be kind of a non-degenerate lottery. So whenever we have these affine pieces that lie strictly, that never even touch the blue curve, that will correspond to real lotteries. So this will be a stochastic mechanism. And just to show you once a multidimensional picture, so here the plane would be the states of the world, two-dimensional, and the mechanism that I'm showing here would be, you tell the agent you can choose any action that lies in this gray set. So in that case, the agent type, if the true state of the world lies in this gray set, the agent gets her first best payoff, but whenever we're outside, you get a lower payoff. So this red-blue curve would be the agent's indirect utility, and the green curve that you see in the back would be the first best payoff. And so this would be the more complicated pictures. I'm not going to use them much. So where are we? So now we have this relatively simple characterization of the incentive compatibility via these indirect utilities. Okay. So in a sense, it's good. So we know every mechanism induces an indirect utility, and we can easily check which indirect utilities correspond to some mechanism. One slight complication is that actually to a given indirect utility, there's not necessarily just one mechanism that induces it. So it's not a one-to-one mapping. So why is that? I think it's easier to see if you assume that the agent, for example, has quadratic preferences. Then if we promise the agent, if we have a stochastic mechanism, that gives them each agent has some utility. But if we replace some lottery by a different lottery that has the same expected value and the same variance, then of course the agent's utility will be the same because the agent has quadratic preferences. So in principle, then you might worry about what's the optimal way to implement a given indirect utility if there are many mechanisms that implement the same indirect utility. And here now, the second assumption that I made on the payoffs becomes relevant, namely that the curvature of the agents and the principal's preferences are the same function. And this is going to tell me that then still the indirect utility completely pins down also the principal's payoff. So for example, if the agent has quadratic preferences, then this would imply that the principal also has quadratic preferences. So if I replace some lottery by a different lottery with the same variance and expected value, then also the principal's payoff would be the same. And the same argument holds more generally. So let me briefly show you. So the envelope theorem tells us that the slope of the indirect utility, the gradient of u, will be exactly equal to the expected value of the lottery M of S. And just from the definition of the payoffs, the utility of the agent will be, well, this gradient u of S, which is just the expected value of the lottery, product the state of the world, plus this expected value of the B term. So this follows just from the definition of the payoffs that we've seen. And this implies that we can write the principal's payoff completely as a function of the indirect utility u. And in that sense, it doesn't matter which mechanism we're using. So the principal's payoff will be just from the definition of the payoff, the expected value of the lottery that we're giving to the agent times G of S, plus this expected value of this B function. And now we know this expected value of the lottery, as we've argued, is just this gradient of u. And we can reformulate this expected value of the B function is just the difference between the utility that the agent gets minus the gradient times S. So we can replace these things. And therefore we get that the principal's payoff, given the real estate S, will be completely determined by the function u and not which mechanism we are actually going to use to implement it. And so this allows us now to write the principal's problem completely in terms of these indirect utilities. The principal is going to choose an indirect utility. So this means a convex function u that lies below the first best payoff h to maximize this expected payoff that he gets. And then we take expectation over the state of the world. So this will be the problem. Now we managed to completely formulate everything in terms of indirect utilities. And an added bonus is that here now we get a linear program in utility space. So all the terms are linear in the utility, which is kind of nice given that we started with a problem where we actually had nonlinearity in the action. So this is something that we got by this assumption that the curvature in the action is the same for the principal and the agent. So this now looks like a fairly tractable problem. So let's see which mechanisms are optimal. The first thing is, well, one thing maybe that's not that tractable is we have these utilities. Not only the utility shows up in the principal's payoff, but also the slope of the utility. So a standard trick to simplify this is to use integration by parts. In one dimension, for example, you could use integration by parts on this term to get a term that's just the utility times the derivative of this, the bracket term, what we have here. But then if you do integration by parts, you get these extra terms at the lower bound and the upper bound of the type space. So these are these green terms over here. Now in a multidimensional setting, you can do this integration by parts, dimension by dimension, or you can use the divergence theorem, but in the end, you get something very similar. Again, you have this first term where you integrate over all of the type space, and here now only the utility function shows up and the slope or the gradient doesn't show up anymore. And then the two endpoints that you had by using integration by parts, now this becomes this extra integral where you're integrating just over the boundary of the type space, these green terms. So for now, I don't want to worry too much about what these exact things are saying. So to achieve that, I'm simply hiding these terms and I'm calling these terms instead nu of S. So these colored terms will be just called nu of S, and I'm going to call them virtual value for utility. So why is that a reasonable name? So we have rewritten now the principal's problem as the principal is trying to maximize the integral of u of S times nu of S. And then we're integrating over a uniform distribution plus some extra weight on the boundary. So nu of S measures how much does the principal's expected payoff change if we slightly increase the agent's indirect utility, right? So if we give more utility to the agent, how does this affect the principal's expected payoff? So this is the principal's value for giving utility to the agent. This is measured by this function nu. And to have some terms easier, I'm going to also use this notation mu for the corresponding measure if you integrate up these nus. Angel? Yes.
Yes, so here is where it matters that the dimension of S is equal to n, right? When you write the virtual utility. I mean, otherwise the interior is empty. You have to use the relative interior, maybe.
A good question. I think I have to think about this more. So I think in the paper I used an argument that then you can go to a lower dimension problem, but maybe
making a change of variables, maybe.
So yeah, so technically I'm not looking at this by assuming we have a density on the type space and so on. And yeah, it's a good question. I checked it at one point, but I have to recheck what exactly one can do with this smaller dimensional type space here. Sorry, I can get a better answer now. Okay, so maybe let's first try to get some intuition for the problem. So this would be a one-dimensional example. I'll just draw some function u here. Suppose this is the virtual value for utility. So what's an optimal mechanism in this setting? So here we have, so by the way, yeah, we have to the left, the virtual value for utility is strictly negative, and to the right, it's strictly negative, but in the middle part for the moderate states of worlds, it's strictly positive. So how then do I choose an optimal mechanism here? So because the virtual value for utility is strictly negative on the left end, this means you want to give the agent a low utility because this translates to high payoffs for the principal. Okay? So you cannot go arbitrarily low because of course you still have to offer a convex indirect utility function. But this means that you try to lower the agent's payoff as much as possible so that it becomes a linear function to the left. And the same applies to the right. But then in this interior part, for the moderate states of the world, you have a strictly positive virtual value for utility. So this means the principal actually wants to give high utility to the agent because it also translates to a high expected payoff for the principal. But then what this gives you is exactly interval delegation that we've seen before. So here you have to the left, you have a linear function. So you try to lower the agent's utility as much as possible. You cannot do that further because of the convexity constraint. You do the same on the right. But for the moderate states of the world, you try to give the high utility to the agent. You do this by giving the agents the first best payer. And you can implement this by interval delegation. And kind of this gives us now just for the one I mentioned, it gives us at least an idea of when interval delegation will be optimal. So whenever it's true that this new function, the virtual value for utility, will be positive on an interval and negative outside of this interval, then the first result is that interval delegation will be optimal. I think Alex has a related result with Amador and Beckwell, where they're assuming, I think in my notation would be that mu is positive everywhere on the interior of the type space. And I think this gives a little bit of a geometric intuition of what's going on here. And for example, this will always be satisfied if the agent has a constant bias and F is log concave.
Very quickly, Andy. So are you going to be able to have results for at least the multidimensional case, and tell us that even for quadratic, etc., whether the optimal mechanism, optimal delegation set is simply connected? Something that would be very interesting to know. That there's the drilling holes is not profitable for the principle.
I don't have the results that I would like to have there, so let me hurry up and try to get what I have. No, I think I should speed up on that. So I don't have a complete answer for that, but I think that's the right question to ask. So let me the first step will be just a characterization of when a given mechanism is optimal. And this is like, for example, results in Amador and Beckwell, where you characterize when interval delegation is optimal. Just to formulate this result, let me first note, so here I'm showing you an indirect utility function, the green curve U. This will be convex. And this is going to induce a partition of the state space such that on each partition element, U will be a linear function and a affine function. So here, for example, it would be that Q0 will be one partition element of the type of the state space because U will be an affine function here. Also on Q1, U will be an affine function. And now between the two, U will be a strictly convex function, but still then you can say every single point is its own partition element, and then U will be affine on this partition element. Mu is this will denote just the conditional measures of mu restricted to those or conditional on being on a particular partition element. And one more piece of notation, I'm going to compare these conditional measures mu, which I get out of the mechanism design problem, to the measures delta. And the measures delta Q will be very simple. They will be either the zero measure or will be a point mass. So for example, on Q0, there will be exactly one point where the U function touches the H function on Q0. And then delta will be a point mass at this particular value S, where the two functions touch. So delta will be for every Q. So this is a partition element of the state space where the utility function will be linear. Delta Q will then be just a point mass at one point on this partition element. And I'm going to compare this measure mu on this partition element with the measure delta on this partition element. That will give me the main characterization of which mechanisms are optimal. So the characterization is then the following: let U be a feasible indirect utility function. This indirect utility is an optimal mechanism if and only if, for almost every partition element, the following two conditions hold. First, this measure mu, which I get out of the primitives, puts the total mass of this signed measure on this partition element will be weakly positive. And the second condition is this measure mu will be dominated in a convex order by this point mass delta. Okay. So I'm going to give you a rough intuition for what these conditions mean economically. But first, let me just point out this kind of is a strange condition that mu is lower than delta in the convex order, because delta is a point mass, right? If you think just about positive measures, like for example, probability measures, it would always be that the point mass is more concentrated than at any other measure mu, and therefore is lower in the convex order than mu. So this condition, mu is lower in the convex order than delta, can only be satisfied if mu is a signed measure that takes on negative and positive values. So why do these conditions show up? So we want to argue that this mechanism mu is optimal. Let's see this direction. So first of all, the result says you can decompose the problem. So here I'm showing you a particular indirect utility. This just has 3 affine pieces. So the first condition says that you can look at each partition element where u is linear separately. So let's look only on this part. And what's the utility that the principal gets? Well, we saw that this is just integrating the agent's utility with respect to this measure mu. But this, because u is an affine function, and mu and delta are comparable in the convex order, this is just the same as here. And now the question is, what would be the principal payoff if instead the principal would be using some other mechanism, u tilde here? But u tilde will be a convex function that lies again below this blue curve. And then you get, because delta is just the point mass at S, and mu tilde lies below the green curve here, the integral of u with respect to delta will be this greater than the utility of the integral of u tilde with respect to delta. And then this condition that mu is lower in the convex order than delta gives us that if I replace this delta measure by mu, I get something that's weakly lower. And this is the argument that the principal's expected payoff, which is the integral of u, is greater than his expected payoff if we were to use mechanism u tilde. And in that sense, then this mechanism u will be optimal because this holds on almost every partition element. This is just to give you a sense why this strange convex order condition shows up here. So to summarize, so the result looks fairly abstract, but so in one sense, it's a good result because it gives you for an arbitrary mechanism a characterization of when this is optimal. It's an if and only if, and you don't need to construct anymore any Lagrange multipliers or something. You just have to check whether those conditions that depend on the primitives of the model are satisfied. I think this is one advantage of working with this indirect utility space. In specific problems, then these conditions can also be simplified. For example, in the one-dimensional problem, you can formulate in a way that you get back Amador and Bechdell's conditions. You get back exactly the same conditions, which is kind of interesting because here you're optimizing over you're checking whether interval delegation is optimal in a class of stochastic mechanisms. Amador and Bechdell, the main part was about finding whether it's optimal in the class of deterministic mechanisms. You get exactly the same condition, which is kind of interesting. And there's some geometric ideas. So the condition is exactly checking whether you can prove your utility, the principal's payoff by kind of tilting the indirect utility function upwards. And it turns out that whenever you can improve the payoff by doing that, you get an even higher payoff by tilting this indirect utility further up. And then we've seen that would again be a deterministic mechanism. So whenever you can profit by moving to a stochastic mechanism, you can also improve by deviating to a stochastic mechanism, starting at interval delegation. I'm going to brief here and talk about the part that Ricardo asked. So you could now also ask in a multidimensional setting, when is it optimal, for example, to have some convex delegation set? Again, the main characterization specializes here to conditions that look very similar to the one we've seen in the one-dimensional problem. It's just for interval delegation, for each point on the boundary, you had to check whether some stochastic dominance condition is satisfied. And now in a multidimensional setting, you have to do this for every type on the boundary. And then one condition that Ricardo asked about was whether you can do better by drilling holes. And the drilling holes is beneficial exactly if mu is strictly negative at that point. And whenever nu is weakly positive, then drilling a hole at that point is not, doesn't improve the principal's payoff. So this is a bit similar to what we have in intervals. So the same thing applies to the multidimensional setting. And again, you can interpret this, it looks complicated, the stochastic combinance condition, but essentially it's asking what happens if I take the payoff function that I get from this convex delegation and I tilt upwards the indirect utility of the agent slightly along some line segment like the black one here. And if this is not beneficial at any point, then the corresponding indirect utility will be optimal. So this is what you can do in terms of characterizing when a given mechanism is optimal. I think I really like results in a one-dimensional setting where you say, I give you some general conditions under which maybe I don't know what's the optimal mechanism, but I know that the optimal mechanism lies within some class of mechanisms. For example, finding general conditions under which you know some interval will be optimal. I think these results are very useful and they would also be very nice to have in the multidimensional. So I found it a bit harder to get them, but the tools in this characterization still seem useful to have this type of results. Maybe I'll just give you a glimpse of what one can do with it. So one could impose the regularity condition that this new function is strictly positive on the interior of the type space. So this turns out to be useful in the one-dimensional case because then interval delegation is optimal. And this is maybe not too strong of an assumption. For example, if you assume that the principal's bias is constant, then this will be satisfied whenever the density doesn't vary too much. So one question would be, okay, what can we say in that setting? What's an optimal mechanism? Yes. Sorry. So I think there's a hope that under these conditions, you can find that the optimal mechanism lies in some class of simple mechanisms. For example, that the optimal mechanism will be deterministic or that it will be convex delegations. That maybe let me just give you one result. So suppose now we're in a two-dimensional setting and suppose that this new function, for example, is concave. Then this result says that a deterministic mechanism is optimal. And in particular, it will be a delegation set that contains no isolated action. So this is something weaker than what Ricardo was asking for. We don't know really whether it's connected or not, but at least you cannot have an isolated action somewhere lying around. And actually, I believe that under this assumption, a convex delegation set will always be optimal. I think we're just still lacking some of the tools that would be useful to prove this result. And in the last 2 minutes, and let me come back to this example that I showed you in the beginning, where we had the uniform distribution and this constant bias. So in that case, this new function takes on a very simple form, namely on the interior of the type space, it's just the value 1, because the derivative of the density is 0. And just on the boundary, it looks different. And the only places where this new function is strictly negative is on this northeast boundaries. So where the agent, where the state is very high. So what the earlier results now suggest is that whenever you have a pooling region, so that several types take the same action, this must take on, this pooling action must include types where nu is strictly negative. So whenever I pool some types, it must be intersect this northeast boundary. And moreover, the previous result told us that here in this setting, the optimal mechanism will be deterministic and no isolated action. And so then it's simply a matter of checking when are the conditions from the main characterization satisfied. And the mechanism that I showed you previously in the beginning was this delegation set where the agent can take any action below the blue curve. And so how do you check this? Well, nu is positive on the part where you delegate. So indeed, you don't want to drill any holes here. And the second condition that you had to check is to satisfy is this stochastic dominance conditions on all the pooling sets. Now, all the types that lie on the orthogonal line going away from this delegation set, they will choose this action because this action is closest to them. So you have to check that on this pooling set the stochastic dominance condition is satisfied. And then to find the optimal mechanism, it boils down to solving a differential equation that determines the exact boundary that you want to take here. So sorry, I was rushing a little bit. Maybe to summarize, I was trying to develop some tools for the multidimensional delegation problem. The key step was having a nice characterization of which mechanisms are incentive compatible. So all the convex utility functions that lie below this first best payoff are feasible. That led to a nice characterization of the optimal mechanism. Also, it looks fairly abstract. It's very general because even in the one-dimensional setting previously, it wasn't completely clear when a particular mechanism was optimal if it wasn't interval delegation. I think the most promising approach or trying to make progress would be to find conditions under which some simple mechanisms are optimal. For example, can we find conditions under which we can be sure that deterministic mechanisms are optimal or convex delegation sets are optimal? Yes, and then I think, so this would be one way, and the other way would be going to specific applications and see whether we can use these tools, for example, to study monopoly regulation if the firm has information not just about the marginal costs, but maybe also about the fixed costs and so on. And I think incorporating outside options, for example, for monopoly regulation seems also an important topic that seems well suited for this indirect utility approach. So thank you for your attention.
Thank you very much. Yeah, Ricardo has to dash off. Thank you very much for staying until now. Yeah, he said if he has any comments, he will send them. So maybe I'll ask Alex if you have any other comments or questions. Maybe we can start with you, and then anybody can ask questions if they have any.
Yeah, if you think back to the original delegation paper by Holmström, he didn't give conditions for interval delegation to be optimal. He just said, suppose we restrict to interval delegation, it makes sense. What's the optimal in that class? It seems like there's sort of a open area here, which is you're kind of been focusing the talk on can you find conditions under which we have convex delegation sets, but it just seems entirely open to say, suppose we have convex delegation sets, how do we characterize the optimum? What's the right, first order condition, calculus of variations, whatever it is. So you gave that one example at the end with the uniform distribution. Do you sort of have more thoughts on kind of that direction?
That's a very good comment. I think I didn't focus on that much yet. I also don't have a very good sense on how to use calculus of variations here, but I think it would be very interesting to start looking at the first order conditions, changing the boundary a little bit. Yeah, that's a good comment. I will try to do that a bit more.
Yeah, maybe in the next paper.
Maybe I don't know how much the tools that I use here are particularly suited for that question, but maybe there's something.
Yeah, I mean, it's almost more like you just raise the natural question of, how would one do it? And yeah, I mean, it could be an entirely different paper unrelated to this, but obviously one that would be complementary to this sort of work.
I was also thinking more about the budget mechanisms that you proposed in your paper. I think it would also be nice to learn a little bit more when they're optimal, when they're doing well. Maybe also slightly complementary, but I think that could also be an interesting way to think about the problem.
Yeah, so if you don't have anything else, is there anybody else who has a comment or a question? Max, you're unmuted.
Yeah, I'm unmuted, but I noticed that Angel raised his hand. I mean, And the reason I'm not struggling, but I'm thinking is that I really wanted to kind of follow up on this earlier discussion that there was about the dimensionality. So yes, can it be done if it's asymmetric dimensionality? But another question is, it makes a difference whether A is larger and versus S is larger. Is if S is no, I had it worked it out, but now I forgot. One of them was easier, I guess.
So what payoff function did you have in mind for the setting?
No, the same as yours. Is just that, well, the motivation when you have dimensionality of S different than the dimensionality of A. If A is larger than S, then can we just take your framework and assume that the distribution is degenerated, with equal n for both of the same, and assume that the distribution is degenerating in some S's.
Okay, very good. So this would be still keeping that A is in vector in Rn, S is in vector in Rn, and just changing the distribution.
Yeah.
I think this works, but I should double check it. I think I think there's also a natural question like why do these vectors live in the same dimensionality, right? Economically, one could think of these are different things. And then I think some settings can be mapped one to here, but I also had trouble with other variations of it. And the question is always, how do you specify the payoff function then if you can't write just this simple inner product and to get this linearity in S?
So that was another, just one last thought. That was another thing, is that this element, why this utility functions, why this form. I mean, that an example would help, maybe some kind of specific example or application.
So in addition to quadratic, or you mean an example that is different from this form?
When does it matter? Exactly what kind of, I'm not too familiar with this. So the good question would be, what does this formulation exclude, for example? When is it restrictive? I'm just, mostly probably talking about the not the content, but presentation. I mean, what would help?
Yes. Yeah, very good. So I spent some work trying to figure out whether there would be a way to generalize it for the agent, and it turns out that there's almost no hope of even getting a tractable characterization of incentive compatibility. So this linearity in the state, which is really important, and maybe not too surprising, like in the multi-product monopoly setting or so, we're always assuming this linearity, but now I have a better sense of why. But I don't know which standard references we are excluding. So that's a good question.
Uncle, just unmute yourself and speak.
Yeah, Andreas, if you want to.
Yeah, I mean, so Max basically, anticipated my question. So I'll try to reformulate it again to see whether we can get something. But I mean, maybe I'm redundant. It's redundant what I'm gonna say. So yeah, I mean, I was one concern. I think it's very clever. No, I mean, how you found a way to generalize quadratic loss functions, in the setting of optimal delegation. But certainly it doesn't work if you have another loss function. You have the state and action. You want to be close to the state with your action, okay? But there is a loss function that is not quadratic. This doesn't generalize, right? So I was wondering whether, there are any other families of problems, okay, beyond the quadratic loss function that perhaps are captured by these utility functions. But again, I think I'm just rephrasing Max's question.
Good. So in a sense, your question already applies in a one-dimensional setting too, right?
Yes.
I mean, I think one motivation was that it captures, you can have asymmetric loss functions, right? Where you have going to the left or to the right can have different costs. So I'm not sure whether I would agree that only quadratic loss functions are captured. So do you, by loss functions, do you mean something like power functions or maybe?
Well, I was just thinking of a distance, like depends on the, I mean, I'm thinking of the one-dimensional case, no? I mean, any loss function that is a power, okay? Yes, exactly what you were saying. If it's a power, I mean, it's certainly going to be true that it's not going to be linear in the state, okay?
Yeah, I think maybe there are results here that within the class of power functions, this might be the only one. Yes.
And the other thing that seems to open, you know, a venue for other set of results is the B function. Okay, so I understand that when you think originally of the problem of loss functions, okay, B is expected to be a concave function. But once we move away from that family of problems, okay, I mean, B could be convex, or it could be concave for the agent and convex for the principal. And actually, you know, for some cookup problems, we may even have transferable utility, which again opens, you know, the possibility of completely new results in this set of problems.
Yeah, that's a good point. I don't have a good sense of what could happen there. Maybe Alex knows it. Like these are all interesting questions already in the one-dimensional setting.
Yeah, I mean, certainly in the one-dimensional setting, there are papers that try to mix delegation with transferable utility. If you don't add enough constraints, then transferable utility can kind of solve the problem too easily. So you add things like, you know, yeah, like no, anyway, it doesn't matter. But yeah, I mean, I think there's this like long literature in the one-dimensional case of just sort of playing around with all the different distribution functions and payoff functions to see like exactly how far we can get things to go. And I think this is, you know, the assumptions that you made on the utility function are sort of pretty standard in that class of, you know, not the most restrictive, for sure.
And maybe coming back to the earlier question about the dimensionality, I mean, maybe I should check this also more. I mean, there are some nice papers that combine, for example, having a one-dimensional state space, but let's say a two-dimensional action space. And then the question is a little bit which actions should you choose to do this? So kind of what Alex mentioned would be one interpretation, one action is the transfer, you choose, the other is the action. But I think there are also other examples or applications. And the other setting, I think there's a paper by Armstrong who's assuming that there is a multidimensional state space, but that the action space is one-dimensional. But in that case, maybe what Max said is, in that case, it's maybe not too interesting to have a multidimensional state space. If you anyhow have only one action to screen the agent, then kind of all these line or hyperplanes, you cannot separate kind of types that lie in the same hyperplane. And so essentially it reduces to a one-dimensional problem. But in a sense, these are interesting questions already, also in the variation of one-dimensional problems.
Yeah, so maybe before Francesco asks a question, I'm just wrapping up the official part. So thank you a lot, Andy, for the great talk. And thanks, well, Ricardo is already gone, but thanks to him virtually, and thanks, Alex, very much for coming. And next week we have another paper by you, but presented by Emir Kamenica. So next week we have comparison of signals also joined with Ben Brooks. So yeah, come back and see that. And yeah, thanks